jag har boken här. Jag behöver nog inte boken i och för sig. Känns bättre. Och bra igen. All right. Next session is about UDP, the other transport protocol that IP uses, and we'll go through the same thing basically as we did with TCP. So, previous session we talked about the network access, we talked about IP, and we talked about the transportation protocols. We went through TCP, and we'll talk about UDP now. If you remember, when we talked about IP, I said that there's a protocol number in IP in the IP header, and if it's 6, it's TCP. Now, if it's 17, it's UDP. So that's what these numbers are for. Now, UDP is a much simpler protocol compared to TCP. Comparing the transport protocols, you can see that we got connectionless protocols, and UDP is one of those, and we got connection-oriented protocols, and TCP is the one that IP is using for connection-oriented protocols. The major difference is then in how TCP is setting up a connection before sending any traffic. So we talked about that in the previous session. That TCP needs to set up, doing a three-way handshake, and needs to set up a connection, and then we'll start sending the actual data. Now, UDP is just sending the data right away. It is not doing any error checking. It's not doing any control that the receiver is actually there. I'm going to start sending the data, and I'm going to be hoping, basically, that the receiver is listening. UDP has a much smaller header than does TCP. A TCP header, as we talked about, is 20 bytes. Now, the UDP header is only 8 bytes. And because of that, we get a smaller overhead, and we get more efficient, if you like, transport protocol. What we have to pay for that is in lack of control and error checking and stuff like that. So, used mostly for application that carry short messages, because we had a shorter, smaller overhead. Does not have any error recovery as TCP has. So as an application programmer, if I'm using UDP and I want it to be reliable, I need to build that into the application. And the application will have to notice that if there is any data that isn't coming through, the application needs to send it through again. UDP is not doing that. So the Ethernet header, 14 bytes. The IP header, between 20 usually, could be much bigger. And the UDP header then is only 8 bytes big. And then whatever data we're sending, whatever higher protocol that is using UDP, and then we got the checksum from the layer 2, in this case the Ethernet checksum. I've just realized that it says IP header layout in the slide. It should be, of course, the UDP header layout. It's a much smaller header, as we talked about. We still have the same source and destination port number, and it's used just the same way as we talked about in TCP. The source number is going to let us know what application has sent this, what process has sent this data, and the destination port is the UDP process number on the receiving side. So used again to differentiate between different processes on the same system. UDP message length is the length of the UDP data, obviously, and there is also a checksum. Now, the checksum in UDP is optional. So when you use UDP, you can decide not to use it, in which case you would put all the zeros in there. If you do use it, it's a checksum for the UDP header and the data that is sent over to using UDP. After UDP header, then we send the data that we're interested in sending. We talked about ports when we did the TCP session. So UDP and TCP is using the ports in the same way. We got a client that starts up a process. It will use a dynamic or random port number. It's 1024 or higher. And then we have a port on the receiving side. If it's a specific server, it could be one of those well-known ports we talked about previously. Now, a socket is my IP address and the UDP or TCP port that I'm using. So on the left side, you can see that the hosts or the clients on this side, their socket is the IP address and the source, in this case, the port number that the client is using. So this is the top one's socket, and this one is the other host socket. Now the server has its own socket with its own IP address and the port is listening for. Yes, as we talked about previously with TCP, some of the well-known ports that can be used in UDP is these ones. You can notice the boot P server and client is the same port that is used in DHCP, which we talked about previously. TFTP is a smaller version of FTP for doing file transfers. SNMP, Simple Network Management Protocol, is used for doing management of network equipment, stuff like that. So some of the well-known UDP port numbers. And that's the end of the UDP part. The next chapter is about ICMP, or Internet Control Message Protocol. ICMP is used by IP as a error and diagnostic program. It is, if you like, a help program for IP. One of the things that you probably have done is using ping. Now, a ping is a ICMP packet. It's actually an ICMP echo request, and we'll get an ICMP echo reply back. So we'll talk about ICMP in this chapter. Again, we talked about the lower levels and IP. We talked about the transportation protocols, TCP and UDP. Now, using IP is also ICMP, or Internet Control Message Protocol. The IP protocol number for ICMP, so in the protocol type in the IP header, if there's a 1, the data going inside the IP header is, or inside the IP packet, is an ICMP message. ICMP is, as I said, built into the IP stack of all hosts. Now, it doesn't necessarily, it has to be implemented, but there are lots of different things that might make ICMP not work. For instance, you could have firewalls, stuff like that, that is not sending through ICMP messages. Also, a thing to remember with ICMP messages is that it is not reliable in any case. A router or a host that sends off an ICMP message will do that as a way of saying that something went wrong in this IP packet you sent. But there's nothing saying that the host needs to do anything. It doesn't necessarily mean that the receiving host of the ICMP message is going to resend it. It's just a message saying that something has gone wrong. It's also a router, for instance, that has a lot of things to do. It might not send ICMP packets through because it has a low priority as a protocol. It is, if I didn't say that, it's not reliable in any case, an ICMP packet. Here they talk about two different ways of doing it, silent discards and informed discards. Now, a silent discard is what you usually use in firewalls and stuff like that. It's where you receive something that is not supposed to be there, or you don't have a service listening to that specific port. Now, if you do a silent discard, which most firewalls and stuff do, you just throw it away. You do not send any packets back to whoever sourced the packet that wasn't supposed to be there. ICMP, if you use that, is going to send a ICMP packet back, telling the sending side that something is wrong. I'm not allowed to send it. I can't reach it. It's not running or whatever. Now, usually we don't want informed discards for security reasons. By listening at informed discards, the other side might find out stuff about what operation system I'm running and stuff like that. So that's why we don't want firewalls and other that kind of security equipment to send that informed discard back to the sender. Now, there are different kinds of ICMP messages. I think I've talked about them previously, but as I said previously, within the IP header, so after the IP header, there will be the ICMP message. Now, the ICMP message itself has a type code to let us know what type it is. There's a code. There are some types of ICMP messages that have several different kinds of messages. For instance, you can see on the right side, there's something called a type 3, which is destination unreachable. Now, there can be different kinds of destination unreachables. For instance, the network can't be reachable, or the host isn't reachable. So within the destination unreachable, there are different types. After the code, there's a checksum, and then there's the actual message. And what that message is obviously depending on what kind of ICMP message we're sending. One of the most commonly used is the ping, or the echo request and echo response ICMP messages, as they're really called. So the type would be a type 8 for sending off the echo request, and it will be a type 0 when the reply comes back. So the echo reply or response. The code is 0. I got to check some. We use sequence numbers to know which one of my pings that I got the response back on. And then there's some data. Usually, for instance, the Windows IP stack is sending the alphabet. So just the A, B, C, D, and so on, just to get some data through. This is a decoding of an echo message. You can see the IP header up here. You can see that the protocol type in the IP header is ICMP, so this is a 1 as a protocol. You can see who's pinging and the destination address I'm pinging. And then inside the IP header, you can see the actual ICMP message, and you can see that it is a packet type, echo, and all the other information's in there. In this case, we're sending 32 bytes of data, which is what the Windows stack is usually doing, IP stack in Windows. Oops. Another ICMP message that you use is the destination unreachable. Now, the destination unreachable is sent off by a router that cannot, or a host that cannot reach that destination. And as I talked about previously, the type code is 3. The code can be different kinds depending on what kind of destination unreachable it is. So if I'm sending something off to a host and it gets sent through a number of routers, and it gets to a router where the router doesn't have a knowledge of that specific network where the host I want to reach is, the router is going to throw the packet away because it can't route it. He will then send off a destination unreachable back to the source, saying that this network is not reachable, or this host is not reachable if he can reach the network but can't get hold of that specific host. I will then send the destination unreachable back. If I'm trying to send something to a server, let's say I'm trying to send a packet to a web server, and the server is up and running, but the service, the actual web server, isn't working. So I can get hold of the host, but the actual service, the web server, isn't working. Now, if I have an informed discard on that server, he will then send the ICMP destination unreachable, and the type code will be port unreachable in that case, because I can reach the network, I can reach the host, the service answering, but that specific service on that port isn't answering. So in that case, it will be a port unreachable ICMP message coming back. All of these, or most of these error messages I get, I'm going to send, in addition to the actual ICMP packet or the ICMP message, I will send the first part, the 64, the IP header, and the first 8 bytes or 64 bits of the actual datagram that was that didn't get through. So I will send the ICMP packet back, and then within that ICMP package there will be the packet that didn't get to where we wanted to go. As a sample of the unreachable message, so same thing here. You got the IP header, again with a protocol field saying that this is an ICMP packet. You got the source and destination addresses, and in this case you got a destination unreachable, and the code is, in this case, host unreachable. So whoever sent this, the lost router probably, is getting to the network. He can reach the network, but this specific host that we're trying to do something again towards isn't working, so it's not up and running. You can also see that we're sending in the data part, the data part is the IP packet that we sent towards the server that isn't answering. So you can see what packet was didn't get through. Some of the codes for destination unreachable, then we'll talk about some of them. Network unreachable or host unreachable. We've got the port unreachable, and there's several other destination unreachables as well. But those are the most commonly used. Another kind of ICMP packet is the redirect. Now, imagine you have your PC on a network, and on that network you have actually not one router, but two routers. Now, usually most hosts, you can only have one default gateway. So the router interface that will take you off your network. So as we talked about previously, if your host, the host will check your destination address with its own address, and it will determine whether or not we're on the same network. If I'm not on the same network, obviously I'm going to send it to my default gateway, to my router, so the router can send it on to wherever we want to go. Now, in this case, this host here doesn't have one router on the network, but he can have only one default gateway. So when he notices he wants to send something to network 2 over to the right side, he will check whether it's on my own network or not, and since it's on network 2, it's not on my own network, so I will send it to my default gateway. So I will send it to router A because that's the router I have configured. Now, when router A receives the IP packet, he's going to realize that to get to network number 2 on the right side, I need to send it to router B. That is, I need to send it back on the same network as I received it on. Now, in this case, we're going to have two IP packets over the same network. I'm first going to send it to router A, and then router A is going to re-encapsulate it and send it back over the same network. Now, that's having the same packets go twice over the same network. So what router A can do in this case is send an ICMP packet back to host A, or the host, and tell host A that, or whatever host it is, that next time you want to go to network number 2, you need to send it directly to router B. By doing this, the host will put that IP address as a specific, it will add it as a root in its operation system. So next time he's going to send something to that specific IP address, he will know that to get to there, I need to send it not to my default gateway, but to router B instead. Now, redirecting, ICMP redirects is one of the things that can be used used by hackers and other people. So it might not be that we allow using ICMP redirects, but it could be used. Well, the redirect message is a type 5. There are different codes as you saw on the previous page. And again, I will send the router internet address, so I will know which one, router, in this case router B, that I'm supposed to send this package to next time. And then, as we saw with the with the destination unreachables, we're going to send the actual packet that was, in this case, redirected, so I know which one it was that was supposed to be redirected. Another ICMP message is the router advertisement. If I don't have a default gateway configured on my host, I can't get hold of my other network. So one way to sort that is to send out, the router can send out something called a router advertisement. We'll usually do that every 10 minutes, and it will tell hosts that it is actually a router on the network, and will let us know what IP address it has. So it's a way of a router to tell the network and the host on the network that there is a router on, and that we can use that. I don't know how much this is used today, but there is a possibility for it. It is also used in IPv6, has the same kind of functions. Now, if a host comes up and doesn't have a default gateway, and I want to know where the router is, the host can send out the router salutation. It's basically a request for the router to let the host know that there is a router on. So I can send out the router salutation. If there is a router on the network, it will then answer with the router advertisement we just looked at. Remember when we talked about the IP header? We talked about the field in the IP header called the time to live, and we said that the time to live is used to make sure that we don't have IP packets looping through the network, going around in a loop, and we won't ever get rid of it. Now, every time a router routes an IP packet, the one thing it will do, it will decrease the time to live with 1. Today all routers decrease it with 1. Now, the router that receives an IP packet which has a time to live of 1, so I will decrease that to 0. If I do that, it means for the router that this IP packet has been in a loop, it's gone around, and now I've taken the time to live down to 0, which means that I'm now supposed to throw it away. So the router doing that is going to throw the IP packet away, and as with most other cases, when I throw an IP packet away, I'm going to send an ICMP packet back to the source. In this case, it will be the time exceeded, or the time exceeded in transit ICMP packet. Now, if I receive time to live exceeded in transit ICMP package, I know that my IP packet has been through a loop, it's gone through a number of routers, and now it's been thrown away. Same thing here as we saw with the others. I got the ICMP packet and then the IP header of the IP packet that's been thrown away. Some samples on ICMP packets. In this case, they're doing ICMP echo request, so a ping. Not much to say about that. Now, troubleshooting with ping. Ping, as we said, is the ICMP echo request and the echo reply. You can send that off, and if the host is up and running, it will answer, or it might answer. Now, there can be lots of other reasons to why a host doesn't answer to a ping. But if it does answer, we know that it's up and it's working. If it does not answer, it could be for a number of reasons. I might not have a route to it, so the router doesn't find it. It might not be on. It could be a firewall or something, or packet filter or something like that, that doesn't allow ICMP packets through. And there can be a lot of other reasons for why the ping doesn't go through. If it does go through and I get the ping back, I know that the host is up and working. The one thing that ping does is it will only tell me whether it's up and running. It will not tell me basically anything else. You've got some options supported in the ping. Now, ping is the application that is actually sending off the ICMP message. Some of the more common options is, for instance, if you're running it in Windows, you can do -T to have it send ICMP package all the time, every time out, until you actually stop it. A usual ping will send 4 pings usually on a Windows. If you want more pings, you can use the -T. You can go in, you can change the time to live if you like. You can change the data, the number of bytes that is sent off and stuff like that. One way to find out what you can do is just write ping on the dot prompt or in the command window. And if you just do ping without any parameters, it will come back and let you know what kind of options you have. So that's the ping. Talking about pings, I'm usually, when I do this, I'll add one thing that is not, that is an alternative, if you like, to ping that isn't in the book. It's called traceroute. And since we talked about time to leave, exceed, and transit, I'll let you know how traceroute works and what traceroute does or gives us that ping does not do. So I'm going to draw a little thing on the slide, on the board. And imagine we have your PC here. It's connected to a router, and I got a network with lots of routers on it. And on the other side, there's the server that I want to get to. And these are obviously connected routers in one way or another. Now, I can send off a ping. Now, if I send off a ping from my PC and to the server, what I'm going, the answer I'm going to get is whether or not this server is up. Now, what I can do with a trace route is that I can trace the route. So I will not only get to know whether the server is up or not, I will also find out what routers my IP package went through. And the way that works is I'm going to send off an IP package from my PC. I'm going to set the destination address to the server address. And in the first 3, usually you send 3 probes every single time. So in the first 3 probes I'm sending, I'm going to set the time to live, the TTL value in the IP header, to 1. Now when I send that off, it's going to be received at my default gateway at the router, and the router will, as all routers do when they route packets, is going to decrease the time to live from 1, which I set there, to 0. Now, when I decrease it to 0, obviously the router says, well, I can't send a packet on if the time to live is 0. So he's going to throw my IP packet away. When he does that, he's going to send an ICMP package back to my PC saying, hey, I've now taken the time to live value down to 0, and therefore I've thrown it away. So the ICMP packet, time to live, exceed, and transit, we talked about previously. Now when my traceroute functionality get hold of that ICMP packet, it's going to write up that IP address that sent that ICMP package back. Then I'm going to do it again. But this time I'm going to increase the time to live value to 2. I'm going to send it off towards the server IP address. It will go to my default gateway. The first router is going to decrease the value, the time to live value, from 2 to 1. And depending on the routing in my network now, it's going to send it to the next hop router. Now, when the next hop router receives it, again, we're going to decrease the time to live with 1, going from 1 to 0. And therefore, this router, again, is going to throw the IP packet back away. When it throws it away, it's going to send the ICMP package back to my host saying, I've thrown you IP packet back. And the trace route functionality in my trace route is going to write up that next IP address from the next router. And again, we'll increase it to 3. We'll send it to the default router. It will decrease it to 2. It goes over here, get decreased to 1, and we'll go to the next hop router, and he will again get it to 0, throw it away, and we'll keep doing that, and we increase the value in the time to live value in the IP header with 1 until we finally get to the server. So instead of just seeing whether the server is up or not, I can also see the numbers of routers and the IP address of the routers. Now, the ICMP package going back to my server, to my host, to my PC, is going to be the one that is closest to you. So that's one of the questions you get sometimes. Why do I only see one side of the router? And it's because when I send the ICMP package back, I'm going to source it from the IP address on the router that is closest to the host. And that's why we see that side of the router. When it gets to the server, obviously the server is then going to send the package back and saying that I don't have. Usually what you do is you send something to the server on a very high port where the server doesn't have anything listening, and you'll get an ICMP port unreachable, and the traceroute program will know that I've now reached the server. So instead of doing ping, you can try to do a traceroute, and it will tell you the routers on the way. Okay. Next chapter is the domain name system chapter. It's the DNS, and the DNS basically and simply is what allows us to use names instead of IP addresses. It wouldn't be very nice and very cumbersome if you would have to go around and remember the IP addresses of all servers. If you want to serve, for instance, and check the news on Aftonbladet, we just write www.aftonbladet.se, and it is the DNS system, or the domain name system, that translates that into an IP address, so that we can put the IP address into the IP header and send the IP packets to the server. So we'll look at DNS and how it works. It's a distributed services. We'll look at different kinds of name servers and how they work. And again, now we talked about the transportation protocols, IP and ICMP. Now, one of the things, the first application protocol, one of the application protocols we're going to talk about is DNS. And the DNS, or the name system, sorry, I'm supposed to use the mouse. DNS is UDP or TCP, port number 53. So one of the well-known port numbers that we should remember is the DNS one. It is using port number 53. Usually, DNS uses port number 53, and is usually, it is using port number 53, and it usually uses UDP. It can use TCP for some things, and I might get back to that later. But well-known port number 53 is DNS. So DNS, as I said, is what allows us to, instead of using IP addresses, right names. So in this case, you got the client, and we want to go to our web server. In this case, the web server is called www.classroom.com. And instead of having to know the IP address of the web server, I just know that name, which is obviously easier to remember. So what DNS does is, I'm gonna, as you can see on the bottom page, is I'm gonna, as a user, have www.classroom.com. That's what I'm gonna set into my web browser. Now the web browser is gonna send this to a DNS server, and using the DNS server, I will get the IP address. Now, as we talked about previously, IP addresses is fine to have in the IP header. Now, since this is an Ethernet, we also need to send that IP packet, within an Ethernet frame. And to be able to send the Ethernet frame, we need the MAC address, the layer 2 address, if you like. And to do that, as we talked about previously, we use the address resolution protocol. So in this case, we use ARP to get to translate the IP address into the MAC address so that we can send the Ethernet frame. But the DNS, it also allows us to do names. And the DNS servers are going to translate that into an IP address. DNS is a distributed services. That is, we use servers spread out through the internet or intranet, if you like, to help us with this. So on the host, there is a application called the resolver. Now, depending on the operation system you use, you might actually go in and configure it on Unix boxes, operation systems. You might go in and actually configure the resolver. In Windows, it isn't as visible. It's still there. You can still do things with it. But the DNS resolver is like an application or process that will help other applications with name solutions. So the resolver is going to send off the DNS request or DNS question, and we will send that to the name server. And the name server is going to respond to it. In the previous case, the host and the name server and the server we're going through were all on the same network. Now that doesn't have to be the case, obviously, and we'll look at that later. The DNS system is built up as a tree structure. So you got a root domain at the top. It doesn't usually, you don't usually see the root domain, but it is there. It is represented usually by adding a final period or dot punkt in Swedish at the end. Now, if I put a period at the end, it will tell the DNS servers that this is what's called a fully qualified domain name. So it's all of it there. And the final period is the top of the tree, so the root part. Underneath the root, we got different kinds of top-level domains. The most common use is obviously COM for commercial businesses, or org for organizations, non-money profit organization. And then obviously you got your different countries, for instance, SE for Sweden, or UK for the UK, or US in the US, and obviously all different nations have their own part. Underneath the top level domains, there are the other domains. So for instance, Global Knowledge has its own domain and also has its own domain name server that will answer to questions about our network and our service that is contained within that domain. So a fully qualified domain name could be the name of the actual server. In this case, the server is called www. It is in a subdomain called Classroom, and the actual domain responsible for that is the global knowledge domain. And the global knowledge domain is using the commercial part. So one of the top level domain used is the com one. There's some new top level domains out. You get extra top level domains every now and then. These are some of them. Not really that interesting. There are different kinds of top level domains, different top level domains. Now, you got different name servers as well. You got the primary name server. The primary name server is where we update our records. So it's where we add the extra, add the information. So the primary name server is a read-write server where we can both go to and find out answers, but we can also change and add records. You can also have one or more secondary name servers. Now the secondary name service is using something called a zone transfer. So the secondary name server is going to go to one of the master name servers, and the master name servers could be another secondary, or it could be the primary name server. So the secondary server is going to go to his master server, and he will find out what records are in the DNS. So if we do changes, we do it in the primary name server, and then we can have one or more secondary name services. And the secondary name services is read-only. So the secondary name service is going to go to one of the master servers that he has and find out what records he's supposed to know about. There's also a one called a cache-only. Now the cache-only is only there to help us and doesn't have any records on its own. It will only cache whatever questions we have. So if I go to a cache DNS server, he will find out the answer for me, and then he will cache the result in his own cache. The actual name resolution service, usually how it's done is your PC or your host, a DNS client. The host or the user on that host, on this client, is typing in a name. And the client is going to send that off to his configured local DNS server. That's why we need to configure a DNS server, either statically when we do the IP addressing, static, or we will get it using DHCP. Now we'll send off the question usually using recursive query. Recursive query means that I want the local DNS server to find out the answer for me. Now if it's a local one and he has the information himself, he will send that back to the client. If it's not the local one, so say we're here in Ericsson and we want to go to Global Knowledge website. Now obviously the Ericsson domain name server is responsible for Ericsson and the Ericsson domain. So he won't have knowledge about Global Knowledge web servers. So what he can do then, he will have information about where I can find the root DNS servers. And the root DNS servers are located in different places around the globe. And he will go to one of the root servers and he will try to find out where to find the closest one of the .com servers, since Global Knowledge in this case is using the com top level domain. He will get the answer from the root server. He will then go to the .com DNS server. He will ask the .com DNS server where I can find Global Knowledge DNS server. He will then go and ask Global Knowledge and that domain server on whatever IP address that our web server is using. He will get that response from the globalknowledge.com DNS server, and when I actually know the answer, I will send that answer to the DNS client, and the DNS client is going to then cache this, and it will save it, and it can use that information to send IP packets off to our web server, or whatever it is he wants to send it to. The DNS header contains some information fields. You got an identification. you got a question count. Usually it will be 1 in the question count. And then I'm going to get some resource records back telling me about the answers about that. So I will tell you the number of counts. The DNS server that is responsible for the actual zone or zone that we're in, the DNS zone, he's the authority. Now, if I have to go and ask someone else, I'm going to get a non-authoritative answer back. I won't go much into the details about the header, but there are different fields in there. This is an example of the query packet. You can see that we have the Ethernet frame, you got the IP one, the IP header, and we can see that the IP header is using UDP, and the destination port is UDP port 53. So this is a DNS packet or DNS question. You can also see what inside the DNS question. Then you can see the DNS header. You can see that this is a query, and the query is for www.globalknowledge.com, and that's the queries being sent off. When you get the response packet back, you can see again using IP and UDP port 53. You can see that this IP address, this domain name has now been resolved into the IP address 206.195.131.240, which is the IP address we can then put into our IP header when we want to send that off. The DNS is a database structure, so on the DNS server we'll have records in the DNS database within the zone. Some of the most common used source records in there is the start of authority, or SOA, which is information about the DNS server, and the zone is responsible for which one to reach if I got a problem, email addresses for the administration, stuff like that. Other than that, the most common one is the address one, the A1. And the A1 is the usual one where I get the name and the actual IP address. So you can see in this case, you got the IP address or the name, London, which is the host and address, and London's IP address is 192.168.1.104. You can have name servers so that we can point to different other name servers. CNAME or PTR is a reverse lookup. There's a top domain called ARPA, or in address ARPA. It is used to find out if I have an IP address and I want to know what the name for that IP address is. So basically the reverse of what we usually use the DNS for. That's used by the PTR record. CNAME is an alias. So instead of having, you can see, for instance, you got www, and www is a alias, a CNAME for London. So you can see instead of having London being resolved into an IP address, and then have a www being resolved into another IP, or the same IP address, I got a CNAME or alias pointing to London, and then I will have to find out that London is actually this one. Obviously that helps if we change IP address. We don't have to change all names at the same time. Some of the records in the DNS database. This is just the same thing, but as a text file. You can see most addresses are, most records are address records. So you can see that router A, for instance, has IP address, and router B has the IP address, and so on. You can see that server 1 is also called Linux. Has the same IP address, the CNAME. Now, if you use a DNS system and you also use DHCP, now, if you're using DHCP, there's no way of knowing before what IP address I'm going to get. So since I get a dynamic IP address, if I go to my DHCP server and I get an IP address sent to me, now because I can have different IP addresses depending on what's free in that scope that the DHCP server is renting out to us, there's no way of knowing what IP address I'm going to have. So there's something called a dynamic DNS, whereas when I get the DHCP address, when I get the IP address from my DHCP server, if I'm using dynamic DNS, I can then go to my DNS and dynamically update the record inside that DNS server. So if I get a specific IP address, I'll go and tell the DNS server that this host and I'm now using this IP address, so that the other users on the network can use that name to get to my PC. If you want to see this happening on a Windows operating system, you can turn on something called the set debug command. Now, if you do set debug in the prompt, it will let you know more. It will give you more information. You can see what's going on when you do this. Sorry, I should first talk about the actual program that do this. There's an application called NSLookup, Name Server Lookup. Now, if you turn on Name Server Lookup, you can, from within the DOS prompt or the prompt, send questions to the DNS server. And the DNS server is going to respond to that. Now, if you do that, you can then, if you like, add some extra to it so to get more information. You do that by turning on the set debug command. There's an even higher level where you get basically all information within the DNS question and answers, and it's a set D2, so debug level 2 basically. Set D2 is going to give you even more information about how the DNS server and what information is being sent over. All right. Do we need a break? Nope. All right. I think this is the final one, isn't it? All right, final chapter then. And the final chapter isn't much of a chapter. It's actually just one slide. And it's something called, in this case, it says port address translation. And this is because Cisco, where this slide came from, is differentiating between something called NAT and what Cisco called PAT or PAT, or port address translation. Now, usually we call it all just network address translation or NAT. NAT is what's being used when we usually, for instance, if you're a home user and you're buying a connection from an ISP, what you usually get is you get one IP address. Now, one IP address isn't enough for me if I want to have 5 PCs at home, or I might have my laptop, I have my stationary, and I have another server or two on the same network. Now, I'm only getting one IP address from my service provider. Now, to be able to use one IP address towards the internet and still use several IP addresses on the inside, we use something called network address translation. Now, network address translation then, in this case, is using port numbers. So we're going to use the UDP or TCP port numbers. So in this case, you have the inside network, so this might be your home network or it might be the Ericsson network or whatever, but the internal network, the one that we want to use less IP address for getting out. So every single one of the hosts within my address, within my network, is going to have its own IP address, obviously. Now, this might be, and most commonly is, one of those private addresses, RFC 1918. the 10 network, the 172.16 to 172.31, or all the ones 192.168, something that we talked about previously. Now, within the network then, I'm going to use all of these private addresses. Now, I have my broadband router or my PAT or NAT router, and on the outside, I only get one IP address. So when I'm sending off a packet, an IP packet from this IP address, for instance, it's going to be sent to my default gateway, to my PAT router. Now, what the PAT router is going to do is going to take my IP address, in this case the server 10612, and he's going to look at the source TCP port number, and he's going to write that up in his table. And then he's going to translate this into one IP address. So the outside, or it's called the inside global address in Cisco terms, but on the other side, on the internet side if you like, we're going to be translated into the 171.69.68.10 IP address. Now, we're going to keep the same port number, the same source port number. If another host wants to go out at the same time, he has his own IP address within the network. Obviously, if I start up an application on this host, that host or that application on this host is going to take its own port number. So we're going to send off an IP packet using the 10616 IP address, and the port number happens in this case to be 1506. Now, when this IP packet gets to the NIT router, again, I'm going to go into the table and I'm going to write up 10616, which is the internal IP address of the host, and the source port that the process is using. I'm then going to map that to the same IP address on the internet side. So in this case, I'm going to map it to the same IP address as the server got, so 171.69.68.10. And I'm going to keep the port number. So looking at this, I will then send it off, obviously, to my destination. Now, looking at this from the outside, it's going to look like it's just one host. It's one host sending off different IP packets going to different servers and using different source port numbers. When the other side, the destination side, when he sends this back, he's obviously going to send it to the source IP address, which from his point of view is the 171.69.68.10 IP address. So he's going to send it to that IP address. It's going to be received by my PAT or NAT router. And then when he receives this, he's going to go into his table. He's going to look at the destination IP address. It's going to be this one, obviously. And he's going to look at the destination port number. He's going to find the destination port number in the table, and he will go back and he will check what the IP address has sent this off in the first place, what actual IP address or IP address has on the inside, and he's going to then map that and change the IP header to send it to the correct IP address on the inside. Now, using this, it allows us to, by using the PAT or NAT router and port numbers, it allows us to have several hosts on the inside, and we're all using one single IP address. Now, the PAT or NAT router is usually, as well as a PAT and NAT router, is also our firewall. So it's usually the same equipment doing that translation. All right.
If the applications use the same port number?
Yeah, because it's a good question, because when we start a process on the host, it will only check on its own system whether that port number is free. So these two might end up by incident or by coincidence to use the same port number. And if we are using the same port number, what will happen is on the PAT router or NAT router, the network address translation router, the first one that comes in with a specific port number. So let's say both of them are using 2031 as the source port number. The first one is going to be mapped with the same on the outside. Now, when the second IP address comes in, using the same 2031. I can't map that to the same IP address and the same port because I can't differentiate between them. So if that happens, what the PAT or NAT router is going to do is going to take another port close to whatever I'm using. So in this case, if I'm using 2031, it might take 2032 or 2029 or something, another port close by. And since I'm writing that up in the table, I'm going to change not only the IP address, but I'm also going to change the port number. So looking at it again from the outside, it's going to look like it's the same IP address using two different ports. When the response gets back, I'm going to go in and I'm going to change not only the IP address back, but I'm also going to change the destination port back to whatever the host was using. This is also why in certain instances, for instance, if anyone has been using a FTP client, if you use an FTP client, you go out through your PAT or NAT router, your firewall, it will do the translation. So when I start up an FTP client, for instance, I will send off my IP packet, and when I send it off, I will get a mapping within the NAT router. Now, one of the things that FTP does is it is using two port numbers. It's using the well-known port number 21 for sending commands. So when I start up a session towards a FTP server, I will send it to the well-known port number 21. It will tell me to log in, stuff like that. When I then want to have actual data sent back to me, so it might be the directory structure, or it might be a file I want to download. Now FTP is going to set up another session, another TCP session. Now usually that TCP session is being set up by the server. Now imagine if I start up the session from within the network, I will send it up through the PAT server or NAT router. It will then have a mapping. Now if the server wants to set up this data connection because we want to send data, he will send that to the IP address on the NAT router because that's where he thinks I'm coming from. And when he tries to set up the destination or set up the session, there's not going to be a mapping in the NAT router because it's not being set up from the inside. So the server trying to set up data connection is going to fail because there's nothing in the NAT table on the router. That's why when you do FTP through a NAT router, you need to have the option passive. You need to tell the server that it's supposed to be passive. That means that the client is saying that, hey, when we want to set up the data connection, I need to start the data connection as well as the first connection because I'm within the NAT router and I need to have the mapping through the router. Otherwise, it won't work. So the NAT might, in some instances, give you problems. Another thing that might give you a problem with NAT is if you have, let's say this server is a web server. Now the web server is going to be listening to TCP port 80. Now, if I don't tell the NAT router where that server is so I can actually make a mapping inside the NAT in the table, in the NAT table, no one's going to be able to reach this web server. Because when they do, they will go to the IP address and they will say, I want to go to port number 80. And since the server is only passively listening, there won't be any mapping in the NAT table. And because of that, it will fail. So if you got a server inside a NAT router, you need to do something called port forwarding. It's where we go into the router and we manually tell it that if something comes into this IP address and it's going to port number 80, I can then do a manual mapping. So it will always be in there, and I will tell the NAT router that if it comes in, I will send it to this, or you will send it to this server on the inside. So we do a manual addition to the NAT table.
How about VPN tunnels going from my client at home through the NAT towards Ericsson's, what we call RVI
Yeah. That depends on the router, actually. Most routers today manage to do this. They're so-called VPN pass-through NATs. On some older ones, you need to open up some ports. So basically need to tell the router that these ports are okay and you're allowed to send these through. So it's a configuration thing on the NAT router. As I said, most of the newer one has support for this built in. It's called VPN pass-through. So you need to be aware of it anyway, and you might have to open some ports to make it work if you don't have support for it. Also, when we talk about NAT translation, I've been told to talk about something called a proxy server. Now, a proxy server is basically doing the same thing. The difference is a proxy server is doing something for you. So if you want to surf, for instance, instead of going to your default gateway to send off your data, you might go to a proxy server. And the proxy server is going to look at what you're trying to do, and he will decide whether you're allowed to do it or not. And then he will start the actual TCP session with the other server. Basically, if in the case of you, if you are surfing, it will surf for you. So he's the one setting up the TCP session, and he's the one that's actually downloading the data. And then he will send that data to you. He will also cache that, or he can cache that. So for instance, if there are several users going to the same website, the proxy server is going to do the surfing. The proxy server is going to set up the session and send the data, receive all the data, and then he will send that off to the clients within the network. So basically, the proxy server is surfing for you if you're allowed to do that towards that site, because that might be some rules saying that you're not allowed to go to that specific site, and the proxy server won't allow you. Also, something that we need to mention is something called the anonymizers that is out there now. There are services out on the internet where you can go to a specific server and he will do the surfing for you. And the reason to do that is hiding your own IP address for one or different kinds of different reasons. You can go to that server and you can then send the server. It's going to change your IP address and send it off to the server you want to go to. The server is going to send it back to that anonymizer server, which will send the data to you. Now that makes it much, much harder to track on the internet, because if something happens on the destination server, the only IP address that it's going to have is the anonymizer server. Now, some of the anonymizer servers keep logs, and some do not. And unless you got a log, and unless you get someone to actually give you that log, you cannot find out what IP address is actually using the anonymous server. So it's a business thing for people. Yeah. Anything else? All right. I will finish up then with the slide that we started out with. The one that we call You and the Network. And this is what we talked about when we started this, was some of the things that we wanted to go through. And we've gone through most of the lower levels. So we talked about your PC. We talked about Ethernet. We talked a little bit about WLANs and VLANs. We talked about DHCP, NAT, stuff like that. We also talked about connections IP-wise between your PC, your router, and whatever server you want to go to. And then, as we talked about when we started, we're going to add to this on the higher levels in a different course. All right. Thanks for listening.